everyone. I am Dr.A.Muthuselvi, Assistant Professor of Mathematics from the Standard Fireworks Rajaratnam College for Women, Sivakasi. In this topic, we discuss about some examples and properties of complete metric space. We already know about the definition of complete metric space. So, in this video, we learned about some basic concepts of complete metric spaces with examples and also know about some properties. Let us go to the topic. First of all, we recall some basic definition. First, we take a metric space, that is X. We define D from X cross X to R. D is a metric space, means D satisfies the basic four conditions. First definition is convergent. That is, a sequence xn is said to converge in X if there is an small x. We take an element from X such that distance between xn comma x tends to 0 as n tends to infinity. So we write as x tends to x means as n tends to infinity. Next definition is Cauchy sequence. A sequence xn in X is said to be a Cauchy sequence if for every epsilon, that is a small quantity which is greater than 0, there exists another number n naught from the natural number such that the distance between xn comma xm is must to be less than epsilon. For every n comma m is must be greater than n naught. Next definition is complete metric space. Let x comma d be a metric space with d as a metric, xn be a sequence in X. Then xn is a Cauchy sequence if and only if for every epsilon greater than 0 there exists a positive integer n where the value of n which must be depends on epsilon, that is n naught which is equal to n naught of epsilon, such that the distance of xm comma xn must be less than or equal to epsilon, that is m comma n which is greater than or equal to n naught. We know that every convergent sequence in a metric space is a Cauchy sequence. So the next property is every convergent sequence in a metric space is a Cauchy sequence. So proof, first of all we take a convergent sequence, that is xn converges to x. Next we take on element epsilon which is greater than 0. Then there exists numbers n which must be in capital N. Another number m which must be greater than or equal to n. The distance between xn comma xm must be less than or equal to distance between xn comma x plus distance between x comma xm, which must be less than epsilon by 2 plus epsilon by 2, which is equal to epsilon. So here which is d of xn comma xm satisfies the definition, so which must be a Cauchy sequence. Next we go to the definition of complete metric space. A metric space is said to be a complete metric space if and only if every Cauchy sequence in X converges to a point in X. That is, a complete metric space means if and only if every Cauchy sequence converges within X, that is satisfies a distance between any two points which must be less than epsilon. Next note, a complete metric space d of x comma xm comma xn converges to 0 as m comma n converges tends to infinity, means then there exists another point in X such that the distance between that point comma xn also converges to 0 as n tends to infinity, that is the sequence xn converges to x naught in X. Every Cauchy sequence in a complete metric space has a convergent subsequence. Since a sequence is convergent if it has a convergent subsequence. So first example, a metric space x comma d with d as a discrete metric is complete. Discrete metric means the distance between any two points is 0 or 1. So first we take a sequence, that is Cauchy sequence in a metric space x comma d. Then we can choose another point epsilon which is equal to 1 by 2, which must be greater than 0 Accordingly, there exists another point n. We take depending on epsilon. For n comma m, which must be greater than or equal to n, the distance between xm comma xn, which must be less than epsilon. Here we take epsilon, which is equal to 1 by 2, therefore which is less than 1 by 2, which implies the distance between xn comma xm, which is equal to 0, since D is a metric space. So distance between any two sequence is 0 or 1. So here we take 0. That means that sequence xn xm, which is equal to with xn and xm are equal. Similarly, we take any sequence, any Cauchy sequence in the metric space, means all the sequences are equal. That is xn, it is equal to xn plus 1, it is equal to xn plus 2, etc. x. Therefore, the distance of the sequence xn comma x, which is equal to 0, which is less than 1 by 2 for every n must be greater than or equal to n naught. Therefore, this sequence xn is a Cauchy sequence, converges to a point x, which must be in x. Therefore, every Cauchy sequence in x comma d converges, which is also in that x, so which must be a complete metric space. Next example, the set or real numbers or set of all real numbers is a complete metric space. Suppose we take a Cauchy sequence xn in R. Then real numbers means it is real numbers. The Cauchy in the real numbers, the Cauchy sequence is also bounded, so it has a convergent subsequence. We already discussed every Cauchy sequence has a convergent subsequence. So next we use a theorem, every bounded sequence in R has a convergent subsequence. So here we conclude that the sequence xn converges itself. So it means that the Cauchy sequence in R converges. So it must be complete. So next example, the space R power k is complete with respect to its usual metric. So first of all, we take the sequence, that is xn1, xn2, etc. xnk. So it must be a Cauchy sequence in R power k, that is k dimensional. Next we take another element epsilon, which is greater than 0. Next we take another Cauchy sequence xn, that is xni, xn1, xn2, etc. xnk means we take in this form xni. So next we find out the cardinality of xmi minus xmi the whole square, which must be less than or equal to summation I equal to 1 to k xmi minus xni the whole square, which must be equal to distance of xm comma xn the whole square. Here xi be the limit of xn as n tends to infinity, means then there exists an integer n such that modulus of xni minus xn, which must be less than epsilon by square root of k for every n is greater than or equal to capital N, for all I is lies between 1 to k. So next we take x. Small x is a set of all sequences x1 comma x2 comma etc. xk. We also find the distance of xn comma x. First we find the distance of xm comma xn. So next we find the distance of xn comma x. So which must be, it is equal to summation I equal to 1 to k xni minus xi the whole square, which must be less than, that is the value epsilon by square root of k the whole square, which is equal to epsilon square by k, which is equal to, that means which epsilon square for every n must be greater than or equal to n. That is xn is convergent, and so R power k is complete. Thank you for watching this video. Thank you.